So we've proven Lagrange's theorem that says that any subset of a finite group will have an order that is a divisor of the order of the big group. This is such a powerful theorem in the theory of finite groups, and one of the ways that you can assess the importance of a theorem is to look at its fallout. What other really important results instantly fall out as corollaries from this theorem? Let's look at several of the corollaries and the fallout of Lagrange's theorem in this video. So first of all, one of the important bits of fallout is it says that any element in my finite group G will have its order, which is a divisor of the order of the group. This is a statement which was true for cyclic groups for number theory reasons, but we now understand is true for all finite groups. Why? Well, in order to assess what the order of an element is, we need to know how many powers of this element do we need to take before it comes back around to the identity. But that number is the same as the order of the cyclic subgroup that G generates. And since that cyclic subgroup is going to be a subgroup of G, Lagrange's theorem says that its order will divide the order of G. Therefore, the order of the element G will divide the order of the group G. So it's not just true that subgroups have orders which are divisors of the order of the group, but elements, individual elements in any finite group, all have orders that are divisor of the order of the whole group. Here's another really important piece of fallout. This actually is a really powerful theorem because what it's going to do is it's going to give me a complete classification of every single finite group whose order is a prime number. This, by the way, is one of the important places that we're working towards this semester. We're trying to understand what all finite groups can exist out in the world, up to isomorphism, of course. And this next result is going to tell me something very specific and concrete about every single finite group whose order is a prime number. Here's the conclusion. Any group of prime order is isomorphic to the additive group of integers mod p, zp. In other words, prime order implies cyclic. What that means, therefore, is that up to isomorphism, there is only one way to make a group with a prime number of elements. And that is a really powerful statement. It actually becomes the cornerstone that we're going to build on as we get further and further down the line to a classification of all finite abelian groups. So why is this thing true? Well, according to our first observation here, if I take a group of prime order and I pick up any element at all inside of that group, the order of that element will be a divisor of the order of the group. But you can probably see where this is going. When the order of the group is a prime numbers only have two distinct divisors, themselves and 1. And so if I pick up any element in this group of order P, either the order of the element is 1, or the order of the element is the prime number P. In the case where the order of the element is 1, we must have picked up the identity element. After all, the identity element is the unique element of order 1 in any group. Therefore, we can rule out that's the only possibility for what happens when the order of my element is 1. In the case where the order of my element is P, since P is the order of the entire group, that means that the cyclic subgroup generated by this element actually generates the entire group G. Therefore, if I pick up any element of my group, either I picked up the identity element or I picked up a generator. And therefore, since my group has a generator, that makes it a cyclic group of order P. And therefore, it's isomorphic to Z mod P via the isomorphism that sends that generator to the number 1. In other words, we can arrange all the elements of my group around a clock face that has P elements in it, and the isomorphism sends G at 1 o'clock position to the element 1 in Z mod P. Therefore, every group whose order is a prime number must be isomorphic to the group which is cyclic of prime order, Z mod P. Up to isomorphism, there is only one way to make a group out of a prime number of elements. That is a really strong statement, and Lagrange's theorem is what gives that to us. It's really a measure of the importance of this theorem to the study of finite groups. Finally, this last theorem is a theorem that's called multiplication in towers. And what I mean by that is if I have a subgroup of a subgroup. So if G is a large group, H is a subgroup of G, and K is a subgroup of the subgroup H, then the index of G, index in G of K, so that relationship that the smallest subgroup bears to the big subgroup, the index in G of K, is the product of the inverse index, in G of H times the index in H of K. Rather than give the detailed proof, let me give a picture proof. It sort of sketches the idea here. I have a big group G, and what I'm claiming here is that when I have a subgroup H and a smaller subgroup K, it's going to allow me to arrange the elements of G not into a rectangle that has nice rows and columns, but now into a three-dimensional rectangular prism that has rows, columns, and also layers, if you like. So the picture here is, say I have my subgroup H in G, which is this first sort of layer in my stack that makes up G. Because of Lagrange's theorem, I know that all of the cosets of H are going to be equicardinal copies that partition the group G into cosets that have the same number of elements as H does. So this next layer we can think of as the coset G1H, the next layer after that G2H, the next layer after that G3H, and so on. And we'll have as many of those layers as the index in G of H. That's one application of Lagrange's theorem on the relationship of H to G. But if K is a subgroup of H, we can also apply Lagrange's theorem to that relationship as well, and deduce that the order of K must be a divisor of the order of H. And therefore, if this is my subgroup K as a subgroup of H, then the cosets in H of K are going to partition the group H into index in H of K many columns in this case. But then, if I repeat that same process in these other layers as well, I will see how the cosets in G of K are going to partition all the elements of G into these little, in this example, 2 blocks stacked on top of one another, just repeated once in each layer, and then repeated the same number of times in each of the layers that makes up G. So every coset of K, the little thing, inside of the big group G, is first of all a coset of K inside of this layer, H, and then is repeated exactly as many times as there are cosets in G of H. This is a theorem that in itself doesn't seem like it's that far-reaching, but it turns out later on in abstract algebra, when we study higher algebraic structures like fields and we study the solutions of polynomial equations, we do Galois theory, which I have a whole lot to say about on YouTube. This fact about the indices of subgroups inside of a group actually takes on this amazing significance when we study extensions of fields and how they tell us how to solve polynomial equations over the rationals. This multiplication formula in towers of subgroups then has an analog as a multiplication formula for the orders of extensions of fields inside of the algebraic numbers. So this is something to hang on to, and then come back much later when you're doing Galois theory at the end of your second semester of abstract algebra, because this really supercharges what we do in that course. There are many other far-flung consequences of Lagrange's theorem that we're not getting to in this video, but which you may want to practice or look at in other textbooks. A good measure of the consequential nature of a theorem is how many things immediately fall out of it as a corollary. These are just 3 of them, but there's many more. Really a testament to the centrality and the usefulness and the significance of Lagrange's theorem in the theory of finite groups.